Okay, now we've been using angle a lot, and we just discovered something pretty interesting, the triangle proportionality theorem. Sometimes it's called the side splitters theorem, but regardless, we're going to use this idea to discover new and interesting techniques to prove similarity. So this problem seems complex, but if you take it step by step, it's actually a fairly simple problem. Just try to make sure as you're reading along, you understand what the problem is saying and the things it is asking you. So, let's read. In the figure below on the left, we have AB over AC equals AD over AE, which equals 4 over 5. And clearly, angle BAD equals angle CAE. We wish to prove that triangle ABD is similar to triangle ACE. However, do not assume that BD is parallel to CE. We want to prove it. So, maybe wondering, why is it saying clearly BAD and CAE must be the same? Well, it's because they're both just the angle A. So, I mean, that's just knowing how to read the angles. So, let's just move on to part A. Suppose I draw some line through B parallel to CE that hits AE at X, as in the diagram on the right. What do we know about triangle ABX and ACE? So, the difference being is that between the two diagrams is that BD we have not shown is parallel. We have just given it some length of 3. And AD is 12. We haven't said anything whether or not it's parallel. That's not something we can assume. However, we can assume that there does exist some point X which, when connected with B, will be parallel with CE. But we don't know what the measures of those sides would be. We do not know if XE is going to have the same measure as DE or not. That's what we're trying to show. Part A asks us, what do we know about the two triangles ABX, ACE? Well, since it's referring to ABX, the one with the parallel lines, this should just be automatic, but we have angles that are the same. So, BXA and CEA are both corresponding. ABX and ACE also corresponding angles. They're the same. And because of that, we then, for part A, know for a fact, that's an ugly A, but we can definitely tell by, of course, angle-angle similarity that triangles A, B, X, and triangles A, C, E are similar due to AA, angle-angle similarity. Okay, so what does that mean? Well, given that AE is 15 in both diagrams above, what is AX? So, we are saying that this entire length is 15. Okay? And we know the sides are proportionate, so let's create some ratios. Now, one ratio we could make is, well, AB that would go along with the side AC. And we can also come up with the ratio AX, which would go along with AE. And then finally, BX over CE. Now, it is asking us what is AX. So let's try to plug in some values to try to find out what AX is. Well, what is AB? AB is 8. What is AC? AC is 10. That is equal to our unknown AX. And AE, which is 15. So, how can I simplify? Well, let's just, first thing I can notice is that this fraction can definitely be reduced to 4/5. 4/5 to make my math a little bit easier. And AX over 15. To get AX by itself, multiply by 15 on both sides. Now, these cancel out. 15 over 5 would simplify into, 15 divided by 5 is just 3. So that lets me know that AX is 12, because 4 times 3 is 12. So that would be the answer to part B, 12. So, hence, what can we conclude about D and X? Well, AX being 12, the entire thing being 15. Let me just erase some of this stuff here. Then, hence, XE by deduction must be 3, because 12 and 3 add up to the 15. Well, what can we then, what is significant about that? Well, if we notice the distance on our leftward diagram, the one where we did not assume that BD was parallel, we still end up getting the same results. That DE, let's see, that DE is equivalent to XE. And, we know that AD is equivalent to AX. So what does that imply? It implies D and X are on the exact same location on the line AE. They are both, in fact, the same points. D and X are the same points. Hence, we can then conclude that BD is parallel to CE. And what can we conclude about triangle ABD and ACE? That they are in fact similar. Just imagine if you take our first similarity statement all the way from part A and replaced X with D, and we would get the same thing. Now, what similarity rule can we create from this investigation? So let me get rid of some of the fluffy stuff here and leave what we have just discovered, or really what we began with in the first place, which is the fact that in our diagram on the left, what did we start with? Well, we started with proportionate sides. So, for example, in this diagram, we know that 8 over 10 equals 12 over 15, which, well, they both end up just being 4/5. They have that same proportion in both. And through that, we also know that the two triangles are similar through all of our work. And because they're similar, well, what did we start with? We just started with the fact that we have two proportionate sides, AB, AC, and AD, AE, and something else. We started with this angle between them, A. Both triangles shared this angle. And that's actually something very helpful to know, because it seems to be that if these two sides are proportionate and this angle between them matches up, we might have a case of similarity. In fact, our new rule is going to be that we have something called side angle side similarity. Again, because we are starting with just the fact that these sides are proportionate, these sides are proportionate, sorry for the ugly writing, and the angle between them is the same. And we get this same kind of concept we've worked with before, but now it works in addition with similarity.